Let's get started. We can look at so we'll look at the concepts that we understood in the morning. So um, in this code demo, we'll look into the following concepts: intersection oriented and non-mark suppression. Probably skip this region proposal. Uh, okay. So here I'm using a library called fill. It's basically below the image show that got linked. So here in this function, I have implemented the intersection over union. It takes in two input parameters, which is the predicted bounding box and the ground truth bounding box. And the first step is basically the predicted bounding box has four coordinates, namely x1, y1, x2, y2. Same for the ground truth bounding box. So basically it's a tuple, and then we are just unpacking them. Then we are doing some sanity check to make sure that x2 is greater than x1 and y2 is greater than y1. So we then do some checks. Then in order to calculate the intersection over union, we should first determine the union of areas. To calculate the union of areas or sum of areas, first we need to calculate the area of each rectangle. So the ground truth bounding box rectangle is given by area G, which is nothing but x2 minus x1 into y2 minus y1. The same for the predicted bounding box area, which is x2 minus x1 into y2 minus y1. So we get the individual bounding box area. If we sum this, then this basically is the union. So this is just illustrative examples. It is not a real world implementation. But in real world, when you are implementing it, you basically has to do all those transformations. To do intersection or union. Yeah, you have heard about alternatives? No. Okay, few of them have read about alternatives. See, all these are low-level implementation for learning purpose. Some guy have already done everything for us. So all you need is to go and install that library and then called model.training. But for academic purpose, that doesn't always help. So you need to understand what actually and below that framework they have implemented. So this is will be all part of this ultralytics package. Then in order to calculate intersection area, then first is basically like we have two rectangles uh, and uh, and then we have to determine the inner overlapping rectangle. So we only have the x1, y1, x2, y2 of those two rectangle, but we do not know how it is overlapping, whether the first bounding box is in the top or in the bottom, or it is in the left or in the right. We don't know which box is in which location. So for that, we should basically get the inner overlapping rectangle's top left coordinates and the bottom right coordinates. That's basically is achieved by these four steps. Then we will get that inner overlapping rectangle's top left and bottom right coordinates. And if you take area of that inner rectangle, then basically that is your intersection area. So now we got the intersection area. Now we also got the union. Yeah, union area is basically the sum of the predicted area and the ground truth area. But what you need to take care of is that you subtract the intersection area. So it is not sum of one rectangle plus another rectangle. It's basically the sum of this subtracted by the intersection. Otherwise, then you double count the intersection area both on the uh, numerator and denominator. So that's what we're doing here. So then we'll get area I intersection area, then we get area U, which is union area. Then if you take the ratio of that two, that's basically your intersection over. Got it right? Let's look at one few examples. So what I'm doing here is I have one bounding box, ground truth bounding box defined with this coordinates. And then I have, let's say, three predicted bounding box. So I'm going to calculate intersection over union between these three predicted bounding box with this one ground truth bounding box. Okay, so for every bounding box in the predictions list, I'm calculating the intersection over union between the predicted bounding box and the ground truth bounding box. Basically, I'm calculating, sorry, I'm calling this function three times, each for one of those three bounding boxes. And then I'm storing that into a list. Okay. Now, how does that looks? See, for example, the blue one is the ground truth bounding box. Then the other three, the magenta, the yellow, the red, or the predicted bounding box. The intersection over union between the magenta and the blue is zero because there is no any intersection. And the yellow has the maximum intersection over union as evident from the visual overlap, right? And the red is having only 20% overlap. So even if you try to apply non-max suppression here, for this person, we have two boxes competing with each other. So which one to select? Of course, we will select the yellow one. Of course, we do not have the confidence information here, but at least going by the IOU score, we will select the yellow one instead of the red one. It's just matplotlib colors. This is just an example. I just put some. So That also we can get. So right. This is basically if you multiply it into the image, probably you will get this. Okay. So this is basically I labeled it here now. This right. Probably this is what I would have done when I was building this coding example. I would have drawn one bounding box that would have got me these coordinates. Then I know what is the image dimension. One second. In the yeah, I have shared the entire zip to Abhi. I think he has uploaded in the LMS. But now also I can share you, not an issue. So I will share this. Can take image. Okay, so this is the image folder I have shared. I think I'll say it. That might be all. Yeah, that's just one image. So if we take the dimension of this image, it's the properties. It's 3858257 right? We multiply 2662. Somewhere there. Uh, the, the top one is somewhere to the region. Okay. Uh, yes. So when you label it, see, it's the same thing. Like you know the dimension of the image, and from that you know like where this yellow box starts, where this ends. Okay. You can probably calculate. So hmm? No, like we got the person's coding box coordinates from the OpenCV in this format. Okay. This is normalized coordinates format, and this is also not. This is CXCY format. Okay. So it says 0.69. If you want to plot the bounding box, you cannot use 0.69 to plot here. So you have to multiply this 0.69 by the image width. The image width is 3858. So that we get a coordinate like 2662, which is the center of this box. The center of this box is approximately 2662. Got it right? Yes, the blue one. Yeah, it's just an sort of an illustrative example just to understand how the bounding box coordinates. Yeah. So if you're already in image coordinates, your bounding box values will be in the range of the image coordinates. It will be between 0 to 3858, 0 to 2572. But in normalized coordinates, it will be between 0 to 1. If you want to go from normalized coordinates back to the original image coordinate, you need to multiply the x into the width and y into the height. Okay. Uh, there is only one. Yeah. There is just only one multiplication. Sure. Again, you have one difference. In this case, this delete by pixels. Sorry. Suppose there is one person, then I draw a bounding box. If it is this line, this one by one, approximately. Right? So this is in the cell coordinate. The same thing I can convert it into normalized. That will be in the range of 0 to 1. Right? That's how I will do. I will call it x multiplied. Okay. That one divided by the same for y. I have to divide by normalize x divided by w by 5. Then I basically get a range between this one translates into 0.65. I'm just making it so. And it'll be like this. That is what you're seeing it in the CVAT export file. Now I cannot plot this box with this red values. So then I will go multiply it by the root, multiply it, multiply it by the root. Then I will get back my original values. Okay. Then with this I can plot. Okay, so then let's skip this selective search. It's not anymore valid or relevant. The non-max suppression is little bit complex. But at a high level, intuitively you can understand. But this is the same logic that we looked in the morning, which is a greedy, yeah, it's a greedy NMS algorithm where we follow this 5 steps one after another. The first one is to remove the box with confidence threshold below a certain value, and then whatever is the remaining bounding boxes, we order them from low score to high score, and then we keep only the highest score box. But in case if there are more boxes with almost the same score, then we remove boxes with higher overlap, and that whatever the overlapping threshold, that is called as NMS threshold. And we repeat this until there is just only one box left for one object. Okay. That's basically is being implemented in this code. So we take in a list of boxes, and we also take in a list of confidence score, and we set the NMS threshold as 0.3. Okay. Then what we are doing is we are doing the same 5-step NMS algorithm, and then we are trying to eliminate all the unwanted or duplicate boxes. So for this, we have 1, 2, 3, 4, 5 boxes, right? 1, 2, 3, 4, 5 boxes, right? Now, let's say the model came up with this 5 boxes for this person, but what would be the actual box? I think it is mostly the green one, right? So uh, then what we do is we do the same non-max suppression. Okay. And what the algorithm has done is it has taken all these 5 predictions. Okay. And then the probability scores, right? I have set it as one is 0 0.9, 0 0.8, 0 0.6, 0.83, 0.7. Okay. Now, what it does is it has picked up 2 boxes. So which one it has picked up? 0, 2, 0, 10, 0. No, this is just a dummy example. Oh, this is not coming from model. I created this manually. It's purely a dummy example just to explain the concept. It's not coming from model. Okay. We'll see how this comes in the model using alternatives. So it picked up 2290, which is the 5th box, then 2090 is the 3rd one. And why it picked up, see, although we had boxes with high confidence score, which is 0.83, 0.8, and 0.9, it still picked up 0.6 and 0.7 because the overlapping might be higher for the other boxes. That's why it dropped the other ones. Okay. So you can play with this code and just try to understand. See, again, this is not what you will be implementing in a real project, because you might be more or less using this framework called ultralytics for implementing object detection. Okay. This is just to understand the fundamentals. Because if somebody asked in any of your examination or anyway or during project, capstone projects, some external evaluators can check your fundamentals. At that time, this might be useful. Okay, so now comes the practical part of it. which you mean uh, we do have collab notebooks using analytics, which it's already shared in the LMS. I will share it now also. So using analytics, you can fine tune, let's say, YOLO V8 onto some custom dataset, some open source custom dataset. This is what is typically also done in most of the industrial use cases also. The only thing is they will train those models on their own proprietary dataset, which is confidential, right? So if you have your company data and you have a specific use case for your company problem statement, okay. In one of the previous batches, there was one person who was working for Target, and that person had a specific use case where they want to evaluate the return of the products and the customers purchasing products online through portals like Amazon. It's a similar thing, right? Target. So they buy products and they return it. So when it comes to the return processing team, they need to evaluate that return. Now, what they typically do is they do it manual checking. So somebody will be taking that product and then they compare it with the reason the customer is specifying. So they may say that it is torn or some coloring discolorization happened, some different reasons. So this team, what they do is they take this image, they manually check it, and then see verify whether the whatever the customer reason is same as whatever is being what is actually is there in the product. So this person did a POC that you can just put one camera and this product can automatically come on a conveyor, take a picture, and then automatically identifies where the problem is, whether there is some torn, damage, discoloration, anything, and then correlate that with whatever customer has explained in that written, right? So this is one specific example it did as a capstone project. And for that, collected images from the target company. So, and then they trained one of these YOLO E. But for learning purpose, like you can use any of the open source data sets, something like this. That's what has been demonstrated in this notebook, how to install analytics, how to import data set, then how to prepare the experiment file. In that experiment file, you will define what classes you want to train. What are the training images? What is the path? What is the validation images? Okay. Then you just call the APIs. Okay. Then select the model. What is your image size? What is your data? How many epochs you want to train? What is your batch size? The batch size depends on what kind of hardware you are training. And that's it, right? So then the library takes care of everything. So it passes the data through the model, calculates the losses, it calculates all the MVP scores for you. So it will print, see for every epoch, it calculates the average precision. Okay. Um, it basically, in order to calculate the average precision, you need to calculate intersection over union. You need to calculate, you have to do NMS post processing. Everything is part of this library. Okay. All you need to do is make sure you configure it correctly and it is working as you expected, and you're not making any sort of mistakes in running this library. Retrain model for object detection. Yeah. So how many of you already know? I think except one or two Ultralytics is new for all of you, right? Okay. So Ultralytics is basically the Swiss knife for object detection. It is the go-to framework for object detection. Um, all most of the heavy lifting is done for you. Okay, with like few lines of code, you could train one object detection model. Okay, and unless you are a deep research scientist who want to deep dive into it, you could build a practical object detection application using Ultralytics. Okay. Compute like Collab will support. So Collab has some T4 GPUs, right? NVIDIA T4 GPUs. Then there is you cannot train on a Raspberry Pi. You can do a deployment onto the Raspberry Pi, but you cannot run natively on Raspberry Pi. You need to do some export. So this Alternative is built on top of PyTorch. Okay, and PyTorch is a deep learning network. It calculates it cannot run on a Raspberry Pi kind of environment. So what they do is they export it as an ONX runtime. Okay? And that basically runs on a CPU. So your Raspberry Pi is mostly a CPU, right? It's not the NVIDIA GPU. Then it can run on a Raspberry Pi. Because the deep learning models to run it natively, you need the GPUs to run it as a nominal speed. Otherwise, it takes a lot of time to run. So those exporting of the native PyTorch runtime into the ONX runtime or the OpenMinnow runtime, it does a lot of optimization targeting the hardware that you are running on. You could do that with your mobile also, no? Or you're doing this 20 circus. I mean, yeah, it's a very interesting learning project. Um, but the same thing you can directly install it in your mobile camera, then put it onto some sort of a gimbal or something like that, and you can run. Because your mobile itself is a sort of a computer, powerful computer. Maybe he's a nerd or like I don't know, he's like kind of a hacker. He wants to explore something. But if you say that is an optimal design, no, like you can do it on mobile also. But that's a good learning project. I really appreciate that. So you can just put one Insta 360 camera. Probably he's taking a 360 view, which is not possible in mobile, and then feeding that into Raspberry Pi. Yes, yes. So what he would have done is he would not have directly deployed a model unless and otherwise there is already a model that can detect traffic violations. But you can just go and do a Google search if there is some already trained model to capture Bangalore traffic conditions. But if you have a model trained on some other country, probably it will flag everything as so, so it will be like all red flagging everywhere. So then probably if there is a specific Bangalore based violation, because even in Western countries, the distance between is also a violation, right? But here we go bumper to bumper. Right? So, so that doesn't work here. So probably if he really is applying, I mean, we need to validate that, but I really appreciate the effort. But let's say he is training a very Bangalore specific violation detection model, then he need to collect some data and then train it according to the Bangalore scenarios and conditions. For that, he cannot train directly on the Raspberry Pi. Probably he can train it on Colab and then export it into a Raspberry compatible runtime files. You understand the flow, right? Then deploy it into the Raspberry Pi. So, I highly encourage that you spend a lot of time in this Ultralytics website. Um, okay. So what does oh, okay. Then maybe that could be one of the pet projects that you can do. Yeah, Gaggle has a lot of data sets. RoboFlow has a lot of data sets. Even nowadays, Ultralytics also they have their own inbuilt data sets. And hmm, sorry,
Hello, sir.
yes.
Yeah, one small information. I just got it a few days back from
So this
through.
RoboFlow, Gaggle, they already have labeled the data set. Okay, first you can start with that. So get familiar. Label is also there. So if you go to RoboFlow, Ultralytics, these two are like very useful uh, frameworks that you need to get familiar with. Okay. Okay. So they something called as RoboFlow Universe, right? It's the open source computer vision data sets and pre-trained models. Explore universe. See here you will have a lot of data sets in different domains. Manufacturing domain, agriculture, construction, sports, self-driving, right? You will have a very simple data set to intermediate complexity level data sets, right? So license plate detection. So this has 10,000 images and this has been labeled already for you. Okay. The only thing is in this, it will only identify the number plate, but it will not tell you the number, vehicle number. For that, you need to have another OCR model. Yeah. Object optical character recognition. So basically, it will identify the alphanumerical numbers. Yes, Kaggle, RoboFlow, even some Ultralytics. Even get labeled data sets. For example, the MS Coco, where most of the pre-trained models are trained on. It's a huge data set. It will be of several GB. Um, but that is also available in MS Coco. Yeah, that's a good question. Probably it's yeah. So first time when you go to the toll, right, and then they have cameras. Sometimes the camera will look here, that guy will come and adjust, right? Yeah, sometimes that RFID also because sometimes that guy comes and then scans your barcode. Hmm? Yeah. So it already has a RFID. So there will be some RFID sensors. We can read that also. Because in Western countries and all, there will be no toll booth, right? We just enter the road, already it will take money from you. I think that might be already there in India. I don't know in which highways it is. Hmm. It is an RFID tag. Some RFID sensor, yeah. So a lot of now I get a lot of tickets, right? And nowadays, if you see, right, the traffic police nowadays they won't stop you. If you go without helmet, they just take a picture of you. That's it. Then they will get the number from the cam picture, and then you will get a ticket automatically. Yeah, they will upload to the database. It has an evidence that you are not wearing a helmet, and they also know your number plate. It will go directly, you will get a ticket. But sometimes I get a lot of tickets which most some of them are like not correct because sometimes the OCR no, it is not detecting correctly. Let's say my number is 5834. Even 5884 also it might think that it is my number. You see, right? Yeah. Even then also I'm not sure if it is giving. I get many incorrect tickets. When I go and ask, he said go to headquarters and correct it. Yeah, yeah, it's not clear like that works.
Yeah, sir, one question. This is Santosh online. Can you hear me, sir?
Now everybody has to have that embossed mic. Yeah. That's specifically for this purpose only because yeah, yeah, the image will be clear because that other one, right? If you have a very high glossy sticker, the camera it will be saturated. Okay, so we are talking about ultralytics. So if you go to docs, yeah, all are free. Um, yeah, for commercial purpose you cannot use. For enterprise use, we cannot use because this is a GPL license. So this is not an one which can be used for commercial purpose. Yes, that you need to find which one is gone by Apache 2.0 or MIT license, then we can use for commercial. So this guys have some licensing model. If you want to use it for your enterprise commercial purpose, you need to purchase that license. But for academic projects, it is okay. They changed the docs a little bit. So okay. Okay. So these are quick start. You can just simply start with pip install Ultralytics. That's what we have done here, right? it connected to a GPU. And then just do pip install analytics, and then you're ready to go. But here I'm downloading some datasets from internet. It's called pothole datasets. It contains some images of roads and potholes, and then they are labeled where the potholes are present, right? So this is again a pet project that people use to for learning purpose. See, I think the important thing is this YAML file. Okay. So this is called as experiment file, and this YAML file is what will be passed into the uh, code, and this has all the information about your dataset path. And within that dataset, if you have the split like train split or validation split, then you have to specify like how you have split the dataset. So then during training, what it will do is the model will be trained on this split, whatever the images are there within that folder, and it will be validated on this folder. And you can also tell like how many classes are there. In here, there is just one single class we are saying, but let's say if you have multiple classes, then you have to define them. Something like that. This classes has to match with our labels, right? That we'll open and see. And that's what I'm downloading. So if you see, so I have downloaded this pothole dataset, right? See now, if you see, we have train and valid splits. In the labels, we will have that text files. Yeah, it's a little bit big. What do you mean by automate? Model. Oh, he's asking manual labeling, you have to read. No. Everything is automatic. And we'll go for vacation. So, so even you just have one sort of a button, and then it will only go and select the data set, download the image, label it, train it, deploy it, test it. Everything. Then what we will do? So there is a little bit of automation be there, but yeah. So here also in this tool, right? For example, some this one, what this? We have this sort of polyps data set is there, where in the colon, right? Sometimes you get this polyps. How do they call it? I don't know how. A little bit of grown regions, right? Tissues, unwanted grown tissues. Sometimes they are non-cancerous, but sometimes they are cancerous tumors. So they grow small. First, it will start with small and then it will grow, right? So there are data sets where they have labeled that hey, this is a cancerous one, this is a non-cancerous. And in order to, so it will be a colon image, I mean visual image. It will be totally inside the colon, but there will be on small polyps will be there. But this model can be trained to identify where that polyps is. Then that's basically the data set. But in order to classify them whether it is cancerous or not, there will be another model to do that. Okay. Yes, it can be applied to medical use cases also. It can be applied on brain MRI images use cases as well. There are some open source medical data sets also. There is a framework called something called Mono, I believe. Yeah, I think he has a little bit. So medical open network for, yeah. So this contains a lot of open source medical data sets. This is specifically developed for medical use cases. I think this was formed after COVID. So during COVID, there was like almost everyone, like how they are doing this agentic AI, right? Nowadays, all Tom, Dick, and Harry is doing agentic AI. At that time, everybody was doing medical use cases. But again, none of them is production ready. Um, so at that time, I think they formed a forum that, hey, we need to standardize this and let's bring all the community like NVIDIA, Intel, Stanford, some sort of research communities. They formed this framework. So they kind of try to standardize. Yeah. Yes. Yes, yes. That's the biggest challenge with medical. Yeah. So they do a partnership with actual hospitals, medical institutes. They, there is one Pune based company. I forgot their name. I'll try to get it later. So they have developed some production enterprise grade AI models for medical diagnosis. Okay. So they have partnership with AIMS, Manipal hospitals, like that. So they will collect the data anonymously, make sure that they have some agreements that they are sharing the patient, and in turn they are getting some reliable, accurate, repeatable AI models that can be deployed into their hospitals and can assist the doctors to diagnose. So it cannot again be automated. Yes. X-ray images, CT scan images, MRI images. like that type of thing. So we also have companies like GE Healthcare, Philips. I think they also will be working. Philips. They also Siemens. So they also will have. See, since it is their device, they might sign some sort of an agreement that they want to use that data to develop some AI models, and they will deploy it back into their device. So similarly, we also, right, we also have a device, but that data is owned by the customer. Although it's our device, they bought it from us. We have access to that, but we don't have the permissions to store that data in ours unless we get explicit permissions from them. So then we sign agreement with the customers. They say, hey, we use your data, we'll develop the AI models, we'll then deploy it back into your machine. Like those kind of partnerships should be there. I don't think, yeah, it's very highly regulated. You mean to say hospital data, you're saying? Okay. Mhm. Mhm. Yeah, yeah. But when you sell it right commercially, okay, okay. Oh, yeah, yeah. Correct. Yeah, it's correct. But during audit, right, when they're scrutinizing you, they will ask you how you got access to the data and what data you trained this model. All those questions you need to answer. If you say no, I just collected through backdoor. I mean, oh, your project. Oh, okay. For yeah, this is always typical questions is very difficult to answer. But to begin with, let's say 1,000 images per class to build some good reliable per class. Means object. You have car, bus, motor, medical. Or let's say body see, in chest X, no, see, chest X-ray, see, see, if you are, let's say, taking blood smear samples and microscopic image, there will be RBC cell, white blood cells, and platelets. Let's say these three. Then I need 1,000 images of RBC, 1,000 images of white blood. It couldn't be in the same, but I need 1,000 bounding boxes of RBC, 1,000 of WBC, thousands of platelets. Then only I can build. So if you have all your images are just WBC and you just have 5 of RBC and 5 of platelets, your model is biased towards WBC. So you cannot reliably say you can detect RBC and platelets. You understand, right? Well, Yeah, so that is why we need to export that model into that CPU environment. So here also, hmm. So yeah, very good question. So here also for each one, they have different size of the model. Second, so they have extra large model. We have large, medium, small, nano. Okay. For in your use case, I would select a nano model. So I wouldn't be selecting a Excel model or L model. But there is also a compromise on the accuracy. An extra large L model is multiple times accurate than a nano model. But your compute prohibits like deploying an larger model into your environment. You can only go up to nano or probably medium model. Of that model itself, right? Yeah, I do not remember the top of my head. It will be in some 100 MB, something like that. Data sets, data sets based on how much images you have. It can be like few hundred MBs to several GBs. So if you have videos, it will easily shoot 2 TB. No, the file size, the model, you'll be saving it as a model file, no? That model itself will be 100 MB, 200 MB, something like that. And nano can be somewhere at 100 MB. But if you go for extra large, it can be like half a GB, 500 MB, 700 MB like that. Yeah, so that is based on the tops or the flops. So based on the parameters, we say no, ChatGPT has 1 billion parameter. Okay. So likewise, if you take this, it might have like 1 million parameter, which means 1 million floating point operations you have to do, right? So you have to do all those matrix computations. So then that many things has to be done to get one predictions. So that much RAM you should have. I think yes, I think they do that. That's why they have this. I'm not a great expert in that. I'm not a very hardware guy. They have this sort of tops information. There will be some data sheet. I think they have changed this documentation page and little bit struggling to get things. Yeah. So you're saying you have a data set and you upload that data set into cloud. Or doesn't have such capability now. But what it can output is it can give you the code, but you have to run the code and create the model. But maybe it can run it if you maybe something like VS Code. You just see basically you say, hey, this is my data set, and you describe your data set. Hey, this is a medical data set. It is to identify, let's say, the cancerous things, and it has these many images. Build me a sort of a model for me. Then it will most probably say that, hey, I will train an Ultralytics YOLO V8 model for this, something like that, and then it will give you a code, training code. And then it knows where is your data, it knows the training script, and it can run it from your command line terminal. Okay. And then it creates a model and then store it there. Yeah, it's possible. Try it. And I don't know if you have a Copilot access or something like that. Yeah, I will try to get that later. So there is something called tops, flops. Yeah. 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 Yeah, yeah. You can train a model or just take some pre-trained model and deploy it in your target hardware and do some speed benchmark. Measure the latency, how much milliseconds it takes per image, right? Then if it is that is meeting your latency requirement and speed requirement, then you can choose the model accordingly. But suppose let's say large model is taking 2 minutes for one inference. Probably your hardware is not capable to run a large model. Then you reduce the size, run nano model. So nano model can run under a second. Then probably nano model is more suitable for you. Okay, got it. Yeah. Then start with medium model, small or medium. Yes. Not necessarily Python, it can also run in C, C++ also. So we export this into a ONX runtime. This ONX is language agnostic. It can run in Windows, it can run in Linux, it can run in Python, it can run in C, C++. That's why they created this ONX format. Because they have different frameworks like PyTorch, TensorFlow. Some uses Python, some uses C++, right? So that's why again they created a forum. They came up with some sort of a communication protocol. So ONX stands for Open Neural Network Exchange Format. Oh, trigger. Again, you can just use a. If you are using a Python-based inference, you can just say load dot model dot ONX. It will load. That will be loaded into the model and then say model dot inference, something like that. So you similar C equivalent code. So in this export, right, you can export it as ONX or OpenVINO. So you will get 3 times CPU speed up. And if you are running in NVIDIA hardware, you can export it as a Tensor RT. You will get 5 times speed. It's very easy. You just have to say model.export and give the format. That's it. You can go. So they support different deployment frameworks. So TF Lite for mobile, NVIDIA, Intel, um, support Qualcomm, those things. See, Google Cloud Vertex is a cloud platform, right? There you can run any virtual instances, mostly Linux-based virtual machines. And you can deploy directly the PyTorch runtime itself if you have a GPU instance. You understand, right? So they have your different types of instances, GPU instance, CPU instance, different sizes. So you have a lot of flexibility in the cloud. What do you mean by that? They have this, see, that's why they have, once you install Ultralytics, you have this different modes, training mode, validation mode, prediction mode, export mode. Okay. First, you will start with train mode. So what you will do, you have a data set. So then before I was telling you, right, you need to define this YAML file where you will say which is my data set path, what is my train image, what is my validation image. After that, you start the training. Okay. Up at the end of this, you will have a model. At the end of this, you will have a model, right? You will have a PT file like this. So YOLO 26 nano.pt. This file can then be used in your inference script. So your inference script will be something like this. This is all the code you need to deploy it in your Google Vertex. So at the end of the training, you will have this PT file. Right? At the end of the training, you will have this PT file. Then if you have a Python environment in your Google Vertex, then this piece of code can be deployed there to run the model. Okay. So if you want, you can try this analytics now, or maybe in a home, but make sure you try this at your home and get familiar with this. I've given one example notebook here in the LMS. You'll find this code, but make sure that you explore this API documentation. Okay. So just to you to read this documentations, there is some quick start guide, and then there is some usage guide. So you can use this Ultralytics after your installation, either in a CLI mode or using Python codes. Okay. So CLI means you just run some CLI commands like this. You can run directly on the terminal. Okay. But since you are like more doing a data science program, you will be preparing a Python collab even run. That's what I have done here, right? After importing the data set and configuring this YAML file, what I have done is I have just called this in a CLI mode. But the same thing can be done in the Python mode also. See, this is actually CLI. So there is a CLI called YOLO. and these are the command line parameters. So what is the task? Okay, so task can be either an object detection or segmentation or key point detection or classification. So Alterytics supports these many tasks. It can support, just 1 second, it can support detection. That's what we are discussing today in object detection. It can also do segmentation, which we will discuss next week. In segmentation also, there are two types of segmentation. One is called instant segmentation and semantic segmentation, which all we will see next week. Last week we saw image classification, right? That alternatives can also do. Okay. Then it can do post estimation, basically like human pose estimations for gesture controls and all those things, eye tracking, all those things, head tracking. Then it can also, an extension of object detection is called OBB. So OBB stands for oriented bounding box, because typically the bounding box are either just without any angle, right? It's just, but if you see that many objects are not always either vertical or horizontal, so sometimes they're tilted, right? So when you draw a bounding box, a vertical or horizontal bounding box for a tilted objects, sometimes it doesn't work very well. So at that time, you can create an oriented bounding box, which means that during labeling and model training, along with the 4 bounding box coordinates x1, y1, x2, y2, it will also estimate the angle of the bounding box. It's not always 0 or 90. It will say anywhere between 0 to 90. Yeah. 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 Not that kind of. So you're saying rotation in data augmentation? No, not this. In this, the bounding box itself is rotated. So in data augmentation, the image itself is rotated. Randomly, it is rotated 90 degree or right or left or upside down like that. In this, the image is same. The label itself is a oriented box, which means it has a certain angle to it. It's not either vertical or horizontal. It can be rotated at any angle. Yeah. Probably, I'm not sure if it is supported in CVAT version. See, like this it will be. Okay. So suppose if you are detecting some specific objects which are, so let's say this uh, sometimes if I want to put this box, right, so what I do is to cover this one, I have drawn one wide box to try to follow me. But if I want to snap fit this, I can do like this. Yeah, yeah. That is next week. That is segmentation. That is called segmentation. That's called polygon, not random shape. Yeah, yeah, it's a random shape, but a more appropriate name would be a polygon. Just the picture. Yeah. 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 Mostly it's called. So here also you will have something called segment anything 2.0. Okay. Now what it will do is, see here. If I draw a box around this, it will automatically convert this into a polygon. Okay, I think it's taken. So what we are seeing is a task, right? Yeah. So then, first is task. Second is in what mode you want to run the analytics. So mode we already know there is train mode, validation mode, prediction mode, export, track, etc. Benchmark. So benchmark you can use it for your speed benchmarking. You can just run this one single line of code. See here onto your hardware and it will print out all the speed and you can select your models. Then we have what model you want to select. So here is where there are a lot of models supported from YOLO V3 all the way up to YOLO 26. These are the evolution of the YOLO models. But it not only supports YOLO models, it supports other architectures also. For example, segment anything model, a mobile SAM, then it has RTTTR, real-time detection transformers. Then it has YOLO world, which means there is an open vocabulary object detection, which means this model is not trained on a specific set of classes. During inference, you can ask the model to detect by giving these classes to the model. You can just give an image and say cat, dog, and let's say car, bus. The models are not specifically trained on cat, dogs, cars, and buses, but it can use its knowledge and then identify all these cat, dogs, and cars and buses during the inference itself. Yes, exactly. She was spot on that it's called the zero shot learning. So these are the models you need to select, and then yeah, this image size again by default these models are trained on 640 cross 640, but you could train it on the full size. You can just increase this size, make it double, let's say 1280 to improve the accuracy of the model. Okay. Then tell what is your data and then how many epochs you want to train. All these are like just an experimental settings. Uh, then you can just run this. Okay. The other questions here. Data sets, right? That's it, I think. We'll take a break. Thank you.